going to be talking about Gibbs free energy. And really, Gibbs free energy is all about whether a reaction will actually happen or not. Just because you have a reaction, it can happen, you can make ammonia or carbon dioxide and water, does not mean it will always happen. So when we look at a reaction, if it's exothermic, we can assume that the products are more stable. And that's because when you have an exothermic reaction, the reactants have more energy than the products. So since we have released energy, we can assume that it has more potential energy, which makes it more stable. Also, if a reaction has a high activation energy, then we can assume that it produces very little product because it's going to require a lot of energy for that reaction to happen. So we could assume that the reactants are stable because we're going to have to put a lot of energy to breaking up those reactants. So let's look at a reaction. Let's look at this one. Ammonia plus oxygen produces this and this. Well, this one is an exothermic reaction because the delta H is negative. So we can assume that NO and water are more stable than our reactants. However, if we inspect it a little bit closer, we actually see that this reaction has a high activation energy. So that means if it has a high activation energy, then it's probably not going to produce a lot of products, even though it's highly exothermic. So how do we know that a reaction is going to happen? Well, let's look at another example. If a reaction is endothermic, we can assume that the products are going to be less stable because we've put energy into them. They're going to have more potential energy, which is going to make them less stable. So if I look at this reaction right here, I go from a solid to aqueous, so I'm dissolving it, and it's going to require energy to do that. So why do these reactions happen if they're not producing something that's more stable and it's requiring energy to actually make the reaction happen? Why do these reactions happen? Well, that's because delta H and activation energy are not the only factors that determine if something happens. We have another variable called entropy. So entropy is actually a measurement of disorder. So if you look at something that is disordered, it has a lot of entropy. So if you look at a messy desk versus a clean desk, the messy desk is going to have much more disorder than the clean desk. So basically, if it's more organized, there's less disorder, and then there's less entropy. So if I look at this right here, I went from a solid to AQ, so I've dissolved it into water. Well, if I look at potassium chloride as a solid, ionic compounds, I have this crystal lattice, which is very, very organized. Well, once I dissolve it into water, then the ions are kind of just everywhere. So if I have a glass of water and I've dissolved some potassium chloride in there, I have some potassium ions everywhere, and then I have some chlorine ions. This has a lot more disorder than the nice little crystal structure that we once had. So if there's an increase in disorder, delta H is going to be positive. So not delta H, I'm sorry, delta S will be positive. So if delta S is positive, there's more disorder. If delta S is negative, there is more order. So this has more order, this has more disorder. So this will be more positive than this one. Okay. All right, so when we're looking at solids versus liquids versus gases, well, in a gas, the molecules are spread out everywhere, they're bumping into the container. In a liquid, they're moving about, but they're moving about in a more confined space. In a solid, they're rigid, they're vibrating, but they are very rigid. So there will be more disorder in a gas, and then more disorder in a liquid versus a solid. So if there are more particles, there will also be more disorder. If we have a larger volume, we're going to have more disorder, and that's because if you have a larger volume, then the particles are more spread out and not as ordered. Entropy also increases with temperature. So all of these situations will have more disorder or entropy. All right, so let's look at some examples. So we're going to predict the sign of delta S in these reactions. So remember, delta S is disorder. So if it's positive, there's more disorder. If it's negative, there's more order. So let's look at the reaction we have here. We have magnesium oxide plus water produces magnesium hydroxide. Well, I could look at the fact that I've got one molecule here and one molecule here. So on this side, I have two molecules, and then I have one molecule on this side. So I can't look at the fact that I've got solids and liquids here. I'm really going to look at the fact that I've got two molecules on this side and one on this side. Well, I went to something more ordered because I only have one particle on the product side. So that means that delta S will be negative here because there's more order. In this reaction, it's the opposite. We're going from one molecule to two molecules. So I've created more particles here, which means that delta S will be positive because there's more disorder in this reaction. All right, so let's look at these. Now this isn't ABC choose one. You have to choose one in each question. So it's actually 3 questions. Okay, so which of the following has the greater entropy? So which one has more disorder? A metal at 273 Kelvin or the same metal at 400 Kelvin? Well, if you increase the temperature, you increase disorder. And that's because the molecules will have more kinetic energy. So they're moving around a little bit more. So this one will have more entropy or disorder. If we look at this one, we have a flexible soft metal or a diamond. Well, a diamond is very structured. So that means that this one will have more disorder. And then we have 2 samples of the same gas at the same temperature, but one has a pressure of 1 atm and one has an atm of 0.5, or pressure of 0.5. So we're comparing pressure here. And if we're comparing pressure, we're comparing volume. So if you have a pressure of 1 atmosphere, that means your volume has decreased. The molecules are closer together than at 0.5. And 0.5, they're going to be more spread out. So that one will have more disorder because the molecules are more spread out. Okay, so I can calculate the change in entropy if I have the entropy of the products and the entropy of the reactants, just like I can calculate delta H. So products minus reactants. Okay, so if I have a reaction for the formation of ammonia, so I make ammonia with nitrogen gas and hydrogen gas. All right, so let's balance this really quick. 2 here, 3 here, and then I'm balanced. All right, so I'm going to calculate it by getting the sum of the products and the sum of the reactants. So when I look at ammonia, I've got 2 moles of that, and my delta S is 193. All right, so products minus my reactants, so N2. I've only got 1 mole of that. I'm going to multiply that by 192. And then I'm going to add that to the other reactant, which is hydrogen. There's 3 moles of hydrogen, though. So multiplied by 131. All right, and then after you do the math, you should get negative 199. And this is going to be measured in joules per Kelvin. So in delta H is usually measured in kilojoules. S is usually measured in joules. And whenever we deal with Gibbs energy, we always deal with Kelvin because we want the temperature to be positive always. All right, so Gibbs free energy, is G. So we know that H is the enthalpy, T is temperature in Kelvin, and then delta S is going to be our measurement of disorder. G is really how we know if a reaction is spontaneous or not. So G determines whether a reaction will just happen or will it not happen. So delta G, if delta G is negative, reaction is thermodynamically favored. Basically, the reaction will happen. It's spontaneous. If delta G is positive, then the reaction is not favored and is not spontaneous. It doesn't just happen. You have to make it happen. But if delta G is negative, this means that lots of products will be made because the reaction is spontaneous. It just happens. So K in equilibrium will be greater than 1. So anytime that we have a reaction and the products are favored, K, the equilibrium constant, is greater than 1. And then on a side note, if the activation energy is high, then the reaction will be slow. It can still be spontaneous, but if we do have a high activation energy in a case that a reaction is favored, the reaction is just, it will happen still, it just will happen very slowly. And then everything will be the opposite if delta G is positive. So H, it measures the enthalpy, and S measures disorder. G will measure the spontaneity of the reaction. So will the reaction happen? Is it going to be spontaneous? Is it favored? And then another side note, watch your units because delta S is measured in joules and H is usually measured in kilojoules.